Okay, we are getting ready to start our next section, which starts with the basics of experimental design. So I'm going to go ahead and zoom in on this. Now we have the basics of experimental design, and you can see I kind of ran out of space here in the line. We're also going to talk about randomization. So that word right there is randomization. Okay. So I'll let you go ahead, and you'll notice this is page 17 through 20 in your notebook. So let's go ahead and turn there. Okay, so we've talked about the difference between observational studies and experiments. So today we're going to go deeper into what experiments are, what are some basic components of experiments. So there are three basic parts of experiments. First of all, experiments need control. Okay. You need a control for lurking variables that might affect the response. Okay, to do this, a comparative design that ensures that only systematic differences between the groups is the treatment administered. So that control is going to help you eliminate these lurking variables. The next thing that you have to have is randomization. So you need to randomize. Now, that's using impersonal chance, which means you can't pick. So using impersonal chance to assign experimental units to treatments. Okay, so notice it's experimental units to treatments. It doesn't necessarily mean a random selection of people. That's not always available for an experiment. This helps to create roughly equivalent groups of experimental units by balancing the effects of lurking variables that aren't controlled on the treatment groups. So again, this randomization is going to help with things you can't control, because it's impossible to control everything in an experiment, so it's important that randomization can just take care of the rest usually. And the third thing is replication. Replication just means to repeat it. You can't do something once and draw conclusions. So make sure you use enough experimental units in each group so that any differences in the effects of treatments can be distinguished from chance differences. Okay, so you need control, randomization, replication to have a good experiment. Now there's some other things that can come into play, but these are three basics that you really have to have. Three principles or three basics of experimental design. So here's our first example here. It says the Physician's Health Study. This study looked at the effects of two drugs, aspirin and beta-carotene. Researchers wondered whether beta-carotene would help prevent some types of cancer. The subjects were 21,996 male physicians. There were two explanatory variable factors, which are factors, each having two levels, aspirin yes or no, and beta-carotene yes or no. Combination of these factors form four treatments shown. On odd number days, the subjects took either a tablet that contained aspirin or a placebo pill. On even number days, they took either a beta-carotene pill or a placebo. Okay, if you don't know what a placebo is, that's kind of like a sugar pill. There were several kinds of response variables: heart attacks, certain types of cancer, and other medical outcomes. After several years, 239 of the placebo group and 139 of the aspirin group suffered heart attacks. The beta-carotene, however, didn't seem to have any significant effects. Okay, so what they want you to show is explain how the three principles of experimental design were used in this study. Okay, so first of all, let's start with this. Right here, they did this almost 22,000 times. There's your replication right there. Okay, also you can see we're looking for randomization. So right in here they talk about how the treatments were randomized. Okay, they didn't let people choose. Okay, and then the third thing is you can see the experiment was controlled. Okay, so we have evidence of control. And for randomize, we're going to put down that treatments were randomly assigned. Okay, they didn't let people pick whether they had the aspirin or not. Okay, so go ahead, we had the replication, about 22,000 people. The experiment was controlled, and they randomized the treatments. That's where the randomization came in. Okay, let me leave that here for a second since I was writing and you couldn't see. Now, since randomization is so important, I want to make sure we hit the importance of it. Okay, so right here we have, what is the main threat to making reliable inferences about cause? We think of confounding as the two groups that we wish to compare differing in some other way than the relevant response. Remember, if you don't randomize, you can't generalize. So again, no randomization, you can't generalize to the population. So the first question here, how do we deal with confounding? Well, obviously it's randomization. Okay, so going on to that, with the randomization, obviously the remedy for confounding is to perform a randomized experiment. And again, we're talking about the treatments being randomized, the assignment of the treatments being randomized, in which some units receive one treatment and similar units receive another. Most well-designed experiments compare two or more treatments. Okay, note, comparison alone isn't enough. If the treatments are given to two groups that differ greatly, okay, bias will result. The solution to the problem of bias is random assignment. So there's hopefully with that random assignment, then you're going to take care of like the differences in the groups, and hopefully the groups kind of look similar. You didn't happen to put all the healthy looking people in one group and the non-healthy looking people in another if you were trying to test some drugs. Now, there's different designs of experiments. So the first one that's going to come into play, it's the most basic, is the completely randomized design. Okay. And the completely randomized design, the treatments are assigned to all experimental units completely by chance. Okay, so you flipped a coin to assign a treatment, roll a die, had them draw out a hat. There's lots of different ways. Now, also, a lot of time in this experiment, there's what's called a control group. The control group either receives an inactive treatment or an existing baseline treatment. So possibly just status quo could also be your control group. So, completely randomized design, the treatments are randomly assigned, you have your control group. Now, a placebo is an inactive treatment. Okay, this could also be a sugar pill. That's an example of a placebo. And then the placebo effect, that's when subjects respond to an inactive treatment. An example of the placebo effect is, if anybody watches the show Mythbusters, they had 2 rooms of people eating Chinese food. MSG makes some people sick. Well, some of the Chinese food, in one room, there was no MSG. In the other room, it was. Well, there were people in the room eating the Chinese food, assuming the MSG was there, who said the MSG was making themselves sick. So in their head, they thought it would, and that would be an example of the placebo effect. Okay, there was inactive treatment or no treatment at all in that case. So what you need to have is a basic diagram when we're setting up our experiment. So pretty much, you're going to start off with whatever your experimental units are. Now, to your experimental units, you need to randomly assign, and yes, you have to write randomly assign here. We don't assume anything. And then that goes to the different treatments. Now, I'm just going to say treatment 1 and treatment 2, but sometimes there could be a treatment 3 or a treatment 4, it just depends. And then, after that, you compare the results. So you would just fill in these blanks, and this will give you the basic mapping for your experiment, which we'll do or give an example of in a few minutes. So our next example says, suppose an experiment is designed to investigate the effects of repeated exposure to TV ads. All subjects viewed a 40-minute TV program that included ads for an iPad. Some subjects saw a 30-second commercial, others a 90-second version. The same commercial was shown either 1, 3, or 5 times during the program. After viewing, all subjects answer questions about their recall of the ad. their attitude toward the iPad, and their intention to purchase it. So first of all, they wanted to start off by what's the explanatory variable and what's the response variable. So what they're using to explain here, the explanatory variable, is the exposure to TV ads. So that's the explanatory. And then what they're measuring, or what the response variable is recall. What did they recall? Okay, that's what was being measured there. Now for this one, they wanted you to list all the various treatments. And for this one, there's 6. There's a 30-second video that you could see one time. There's a 90-second video that you could see one time. There's a 30-second video that could be 3 times, and a 90-second that could be 3 times. Going back, 30-second 5 times, and 90-second 5 times. Okay, so you can see you have each of those right there. Now, the last thing we're going to talk about today, we're just going to kind of finish up talking about the types of experimental design. Well, one we've pretty much gone over. That's the completely randomized design. The next type of design is the experimental block. And the third is the matched paired design. Okay, so we're going to go ahead and just talk about the randomized comparative design in this one, and then we're going to move on. Okay, so right here, a farm product manufacturer wants to determine if the yield of a crop is different when the soil is treated with 3 different types of fertilizer. 15 similar plots of land are planted with the same type of seed but are fertilized differently. At the end of the growing season, the mean yield from the same plots is compared. So first of all, they want the experimental units. Well, the experimental units are just the plots. That's what's being tested. Okay, what they're using to explain in this one, different types of fertilizers. They want to see how that works, so that's just fertilizers. The levels, there's 3 different types of fertilizers, so therefore there's 3 levels. They want to know what's going on in this one, like what are they measuring? Well, obviously it's how much they're producing, so that's actually called mean yield. My best friend married a farmer, so I know a little about that. And then lastly here, the design is completely randomized. Okay, so what I would like you to do is try number 3 on your own. Okay, and this is one we can talk about tomorrow. And then the last thing we're going to talk about is example 4. Okay, so with example 4, suppose we are interested in designing an experiment to see how caffeine affects heart rate. Here is our initial plan. Measure initial pulse rate, give each student a Mountain Dew, wait 30 minutes, measure the final pulse rate, and compare initial and final pulse rates. Right there it says, are there any problems with this plan? What are some possible lurking variables we should be aware of? To me, what they do in those 30 minutes, I'm going to say the activity done in the 30-minute wait period. That's a big deal. Okay, if someone goes running and someone sits there, there's going to be a big difference between their heart rate. Okay. Now to me it says propose some solutions to the problem. I'm just going to say use control to keep the activity constant.